Hello students, welcome back. We are done with sections 1 and 2. We talked about matrices, saw some examples, and defined the algebraic operations, addition, scalar multiplication, and transpose. Now, the hardest of the bunch, let us talk about the matrix multiplication. This is the definition. Matrix A, which is an m by n matrix, which I'm highlighting now, and matrix B is n by p matrix. And the product, A times B, is an m by p matrix and defined like this, exactly like the scalar product. Indeed, the scalar product is embedded in there. Please note that I highlighted n here and there. They have to be the same. So we have m by n, n by p, mn and p, n's collide and disappear, and we have m by p. That's what we have, m by p. And how do they collide and disappear? Through this. So arbitrary entry, ik entry, is defined by the dot product of this row vector times column vector. Like this. The dot product or scalar product of row vector times column vector, and row vector is coming from the first matrix A, and column vector is coming from the second matrix B. And in order to have valid scalar product, we have to have the same dimension. They are both n-dimensional, as I highlighted over here and then there. How does the scalar product work? A1 times B1, A2 times B2, A3 times B3 all the way up to AN times BN, and then add them all up as we have over there. It's a scalar product. What if we have m by n matrix and then something different times p matrix? Like for example, there are 5 columns here and then only 4 rows here. That means this is 5-dimensional vector and this one is only 4-dimensional, which means the last entry over here will not have corresponding entry here to multiply with. So the scalar product is not well defined. Unless we have 2 same dimension, the scalar product will not work, and that's why we need this n and n to be the same. Okay, so much about the definition and the theory. Let's talk about an example. Here's a concrete example. We have a 3 by 4 matrix times 4 by 2 matrix, so 3, 4, 4, 2. So the answer should be 3 by 2 matrix, as you see over here, 3 by 2. Well, I did the computation here, but if you can follow, great. If you can't, well, in case you can't, let's really slow down and go through this computation and pretend you cannot see the answers here, at least for now. Okay, let's do the computation. Very first entry comes from first row, first column. And let's take the dot product of those two. First entry times first entry. We need 1 times 0. And I'd like to have it in blue. Okay. So first times first. Second times second follows. So we get 0 times 1. Next, third entry times third entry. Finally, fourth component times fourth component. If you calculate what you get 0 plus another 0. Oops, excuse me. This should be equality. 0 plus 0 minus 3 minus 2 times 2, 4. So this is negative 7. And is that what we have over here? Negative 7. Let's do this one more time. Okay. We're done with first row, first column. So let's go to next column. So first row, second column this time. Again, we are doing the scalar product. So first entry times first entry. So 1 times negative 1 And I'd like to have appropriate color here. Okay, let's keep it red. Second component times second component, 0 times 0. And then third component times third component, 1 times 4. Now, negative 2 times 1 is the fourth entry plus times another fourth entry. Fourth entry of this row, fourth entry of this column. What do you get? Negative 1 plus 0 plus 4 minus 2, which is, is it 1? Yeah, that's right. 4 minus 3, that's 1. Okay, all right. Can you follow? Just in case, let's do it one more time. Okay, first row, first column, second column, all done. So let's go to the second row this time. And then first column, and then of course we're going to take the dot product. First entry times first entry. Give me a moment, I need green here. Okay, all right. Now second entry times second entry. And then third entry times third entry. And then fourth component times fourth component. So you get 0 plus 1 minus 3 minus 6. Is that right? And then am I getting negative 8 here? Yes, we are getting negative 8, as you see over there. With its first 3 entries, and then still 3 more to go. We need second row, second column, and that's over here, and so on and so forth. That's how you do matrix multiplication. So each matrix multiplication has a bunch of trivial computation in there, so it can be really tedious. How about using technology aid here? If you use handheld calculator, I don't think it'll be very helpful because there's so many things to punch in, and each time you punch, if you miss punch, you get garbage. And I think in this kind of problem, it's gonna be safer, not only safer, but also quicker to do it with paper, pencil, and your brain method rather than punching the calculator. Now, there's some computer algebra system that can really help you in matrix computations, but I'll talk about it in a separate video. As a matter of fact, that's gonna be an important video. Okay, let's move on. There are some answers here, but I don't know whether you can follow all that because I skipped some steps. Okay, here's another example. This time, matrix times a 3 by 1 matrix or column vector. And if I do that, the result is also a column vector. And this kind of observation is rather important. You started off with a 3D vector, and after matrix multiplication, you ended up with a 4D vector. So matrix multiplication can be considered as a kind of function from 3D real space into 4D real space in this particular case. And depending upon the number of rows and columns here, 3D can go to 5D, or 17D can go to 11D. You can consider all kind of variations. In any case, let's do maybe 1, maybe 2 computations, just for demonstration purpose. Okay, how do we work it out? First row. Oops, what did I do? Excuse me. Wrong key. Okay, all right, I got it back. And okay. First row times first column. What do you get? 2 times 2, that's 4. And then plus, oh, I'd like to have blue. Okay, negative 1 times 7, so this becomes minus 7. And then 4 times negative 1, so this is minus 4. And what do you get? Negative 7, right? 4 minus 4 cancel each other out, we get just negative 4. What if we do second row, this column? You see, first row is already done because I don't have any further column. So we don't have second, third, and fourth column to work on. So we just go to the next row and the only column. And then let's take scalar product. 1 times 2, that's 2. And then 1 times 7. And then 0 times negative 1 plus 0. And that's equal to 9, isn't it? Let's take appropriate color here. And indeed, we have 9 over here. You can do this 2 more times, and then you're going to get this one and that one as well. I'll leave the detail to the students. In any case, if you multiply matrix by column vector, then the computation is easier, much easier than multiplying another big matrix. But theoretically, it's important. This matrix multiplication can be considered as a function from 3D space to 4D space. In this particular case, it's going to map from Rn to Rm. Okay, final example is a undefined case. This is 4 by 3 matrix, and not 3 by something, but 4 by 2 matrix. 4, 3, 4, 2. It's not going to work. We need n by n and n by p. So I highlighted accordingly. Please note those. So this is undefined case. Those are matrix multiplications. As for some further examples and further computations, I left several problems as a homework problem from our textbook. So I'll leave it at that. And here, let's just move on to some further examples of matrix multiplication. The second simplest example, the identity matrix. What's the use? It works as a multiplicative identity. As you can see in this example, if you multiply I times any matrix, you get that very matrix whenever the matrix multiplication is well defined. This is 3 by 2 matrix, so I need 3 by 3 identity matrix here. And then if you multiply, you're going to get the original entry back. By the way, for identity matrix, the ij entry is traditionally written as delta ij. Previously, what did we do? We used expressions like aij for a, bij, cij, those kind of things. But for identity matrix I, typically we use delta ij for historical reason. As a matter of fact, this delta ij is called Kronecker delta, named after late 19th century German mathematician Kronecker. If you want to know a little bit about it, then you can read through this Wikipedia link, and then maybe you can study more about history. In any case, that's the identity matrix. Okay, that was such a simple example, and I didn't really want to spend too much time on it. Let's move on to the next topic, algebraic rules. We have associativity, multiplicative identity, we just talked about it, distributivity one way or the other, and then I don't know what we should call associativity or commutativity, I don't know. If you have scalar multiplication, it does not matter in which order you multiply, whether you multiply to b first or c first, or after calculating b times c, does not matter. They're all the same. That's what the scalar multiplication is talking about. Now, how about the matrix multiplication? Does it matter? Does the order matter? Yes, it does. And the commutative law does not always hold. That's why I needed this distributivity and that distributivity as two separate rules, because I cannot switch the order of multiplication. In some cases, AB is equal to BA, but not in general. And I gave you a beautiful example here. Very, very simple example. A is 0, 1, 0, 0, and B is 1, 0, 0, 0. And I'll leave the matrix computation to you. Calculate the product A times B, and then B times A, and see if they are the same. They're not going to be the same, of course. That's why I listed as an example. The answer key is hidden here, as you can see from this arrow box, but I'm not going to open it. I'm going to ask you to do some computation on your own. Another interesting topic, zero divisor property. A times B is equal to 0. Does that mean either A or B is equal to 0? As a matter of fact, the zero divisor or zero product property was true for the real number arithmetic, and also for the scalar product. Excuse me, did I say scalar product? No, excuse me, scalar multiplication. Sorry. But for matrix multiplication, no. Scalar product, also that's no. A dot B or vector V dot vector W equal to 0 means they are orthogonal, they are perpendicular. And then matrix A times matrix B is equal to 0 is still something different. As a matter of fact, this matrix A times that matrix B, if you do it right, you're going to get 0. See? Calculate this AB, then you're going to get 0. A times B will turn out to be 0. First row times first column. What do you get? 0 times 1, 1 times 0, that's 0. Otherwise, you're multiplying bunch of 0, 0 times something. So all killed. So yes, A times B is equal to 0, but neither is 0 at matrix. How about multiplicative inverse? Multiplicative inverse doesn't always exist either. And counterexample, as a matter of fact, same example here. This one has no multiplicative identity. Multiplicative inverse, excuse me. What if multiplicative inverse exists? If it exists, then you're going to get this kind of contradiction. A inverse, let's suppose this exists, times AB. Turns out AB is equal to 0, so this is equal to A inverse times 0 as you see down here. And of course, A inverse times 0 matrix, so the answer should be 0 matrix. But then again, A inverse times A first using the associativity, then A inverse times A is identity I. So this is I times B, so we have just B. Does it mean these two matrices, B and 0 matrix, are the same? No, not really. We have non-zero entry there. So there goes a contradiction. Well, I'm not going to spend too much time on proving anything on matrix multiplication. See you again in an optional video, and let's move on to the next topic, the transpose rule. A times B transpose is not A transpose times B transpose. We have to flip the order. AB transpose is B transpose times A transpose. How do we prove it? Okay, that's a long story, and I think I posted the proof here, but it's a little bit hard to follow. Let's meet again in an optional video to discuss these proofs. As for matrix addition, vector addition, and scalar multiplication, I left most of the rules as homework because I think everybody should be able to handle. Matrix multiplication, that's a little bit different. So I'm leaving most of them as optional topics. So if you're interested in proof, watch the optional videos.